This is the first of several lessons on file archiving and compressing. This lesson is about archiving in general and discusses why you might want to use archiving. Archiving files and compressing files are two different things, but they're often used together. When you archive a group of files, you collect them together into a single file or some other form where they're all maintained as separate entities, but they're combined together in a group for easier management. A disk directory is, I suppose, a simple form of an archive. Basically, an archiving program will combine a group of files into one file that you can copy for storage or for transmission to another location. There is a companion unarchiving program that goes with it that can be used to extract the original files from the archive and restore them to their original state. This restoration may retain the date and timestamp of the original files, or it may use the current date and timestamp. In any case, it creates a new set of files that are identical to the ones that had been archived. You compress a file by making it smaller. There are many compression algorithms. Some work better for certain kinds of files than they do for others. Some of the compression algorithms pack the data away in a form that can be restored bit by bit to its original state. Others will compress the data into smaller packages if you allow for some percentage of loss. This is often done when compressing audio and allowing the quality to be compromised for the sake of creating a smaller compressed file. Just like archiving, file compression is a two-way street. The compression program uses an algorithm that compresses the data into a form that a companion uncompressing program can restore to its original uncompressed form. Compressing and archiving are used together. Doing this makes it possible to store a collection of files into a single file that is much smaller than the sum of the sizes of the original. This can be done in a single process, or it can be a two-step procedure, and there are two fundamental ways of doing it. One approach is to compress each individual file, then have the archiver pack away the already compressed files into an archive. It is also possible to create a single archive file containing all the uncompressed files and then use a compression routine to compress the archive file. Both of these methods work, and one seems to be about as good as the other, but you must be careful to reverse your direction when you take them back out. For example, if you archive first and compress second, then you will need to uncompress first and unarchive second. There are lots of reasons to archive and compress. The most recognizable use is to perform data backups. If you're going to make safety copies of things, it's advantageous to make them as small as possible, and it's convenient to combine several files into one to simplify storage. A common reason is for the transmission of data from one location to another. If you create an archive, then you have one file to transmit and verify for correctness. If at the same time this file is compressed, then less data has to be transmitted. And in some cases, the compression can reduce the size of a file by 80% or even more. Sometimes you may just want to save some space. If you have a directory full of files that you don't use very often and these files take up a lot of space, you may find it convenient to compress the files. And you may prefer to combine them into a single archive, so then you can just extract and expand the one you want when you want to use it. An example of this are the man pages. Most of them are in a compressed form and are expanded by the man utility as you ask for them. There are special archivers that keep files under lock and key and only lets one person at a time check them out for modification. Others can get read-only copies, but with only one person being able to make modifications, it's very useful when a group of people are working on the same files. This is commonly done when a group of programmers are working on a project, but it also is convenient for other shared files such as documents or diagrams. There are several different Linux programs that can do these jobs, and you need to know something about them. Not only do you need to know what your options are when you want to pack something away, but you need to know how to extract the files when somebody sends you something that needs unpacking, and that's the purpose of the next few lessons. This lesson describes the compress and uncompress utilities. This directory contains a number of files of all different types that can be used to demonstrate just how this program works. Here we have some image files, word processing documents, shell scripts, and so on, and you can see the files vary in size. The compress utility uses an algorithm known as adaptive limple-ziv coding. For each file named on the command line, it creates a compressed file and replaces the original file with the compressed version. So you can recognize the file type. It appends an uppercase Z as a suffix to the existing file name. As an example, let's compress the file named nuncast.doc. The size reduction here is very good. It's normal for word processing documents to shrink dramatically for just about any compression algorithm. Let's do this whole directory. Now you can see that it refused to compress the file that was already compressed. Also, notice that the PNG and JPEG files were not compressed. There's already a good bit of internal compression already in these file types, and if compress can't improve on something, it leaves it alone. By the way, the file utility doesn't look inside compressed files to see what's in there. It just recognizes the compressed type. All the files in the directory can be restored by a single command. A lot of work on compression and uncompression is done by a lot of different people. You can get the version information for compress with the V option. Here you can see that the original version of this software was released in 1985. There have been a couple of updates since then. This version was compiled in the year 2000. Of course, this being Linux, I have the source code and could compile my own version to move that date up, but there's no real purpose in me doing that. Not unless I want to change the way it works. This algorithm is called adaptive because it changes on the fly if necessary. In the middle of compressing a file, it checks to see how well it's doing, and if it concludes that it could do better, it makes some adjustments and starts over. That is, it adapts to whatever situation it finds with the data in the file. It's very efficient, and as you can see, it's very fast. By the way, this is the algorithm used by man to store the man pages. If you look in the directory containing the system man pages, you'll see that the files all end with a uppercase Z. This lesson describes zip and unzip. There is more than one advantage to using these programs. Not only do they do a good job of compressing and archiving files, but they're cross-platform. Files zipped on one operating system can be unzipped on another. That goes for Unix, VMS, MS-DOS, MS-Windows, OS2, Minix, Atari, Macintosh, Amiga, and probably some others. This is actually two programs. The zip command will produce compressed archives, and the unzip command will extract the files from the archives and restore them. The zip utility is designed to combine several files into one compressed file, but it can just as well be used to compress a single file. Now here's how it works. This is an image file. It's the raw data resulting from a dump of an X window. The zip utility leaves the original file intact, so you have to provide the name of the compressed file on the command line. It's always the first name on the line. You can specify the .zip suffix, but if you don't, zip will add one for you. All of the other names on the command line are the names of files to be compressed and added to the zip file. In this example, I'm zipping just the one file. A raw image file like this has lots and lots of repeated pixel values, so you can see that it compressed down to a mere shadow of its former self. It's just as easy to zip every file in the directory. Here, I'll get rid of this zip file and create a new one with all of the files in it. Zip compresses each file individually, then stores the compressed files in that zip file. You can see that some of the files compress more than others. In fact, a couple of them won't compress at all. But whether or not they compress, they are all stored in the zip file. Here's the size of the zip file. Copying this one file gives you a copy of all of them. Let me move to an empty directory. And copy the zip file to this directory and unzip the file. Here are all the files, the same as they exist in the other directory. I didn't really have to copy the zip file to this directory to unzip the files here. I could have just used the path name of the file and unzipped it from where it was. You can use the R option on zip to include all the subdirectories. R stands for recursive, and it will cause zip to descend to all subdirectories and zip every file it finds. When this is done, running unzip will recreate all the directories in the new location and will populate them with all the files. There are lots of options to zip. It's not possible to remember them all. There's a man page, but once you learn how to use zip, you can get a quick refresher on the options by entering zip with nothing else on the command line. As you can see from this list, it has two types of recursion. It can also handle symbolic links, can update files in an existing zip file, and has an encryption algorithm that requires a password before it can be unzipped. In particular, notice the L option that converts line feeds and carriage returns. You see, each line of plain ASCII in Linux ends with a single carriage return, while in DOS Windows, each line ends with a carriage return and a line feed. You may want to consider this if you are zipping files that are to be unzipped on a Windows machine, but you must only use this option for text files. This kind of translation will destroy other types of files. This is exactly the same translation that occurs with an FTP file transfer, and you choose ASCII instead of binary. The unzip utility also has a long list of options. And there is another utility called zipinfo that will look into a zip file and report to you what it finds there. Without any options, it works like the L option on ls on a directory. And it also has lots of options. This lesson is about gzip and gunzip. Sometimes it's hard to know how to pronounce these things. I've also heard them called gzip and gunzip, and that's more like the GNU tradition of pronouncing things. I'm just going to call them gzip and gunzip and let you sort it out. These utilities work more like compress than they do like zip because they don't archive, they simply compress individual files in place. Gzip will remove the existing file and replace it with a compressed file of the same name but with a gz suffix added. For example, the screen dump file can be gzipped like this. Now this file can be restored to its full size with gunzip. By the way, you'll see compressed files with a single lowercase z as the suffix. These are files in this same format, but they were compressed on DOS Windows or some other operating system, but they use this same algorithm. They're in the same file format and can be handled just fine by gunzip on Linux. It's only the suffix that's different. Also, like the compress command, all the files in the directory can be handled by a single command. This algorithm does everything it can to compress files that won't cooperate, even if they're able to reduce the size by only a few bytes. There are 3 different ways to restore all of these files to their original names and sizes. You can use gzip with the D option, you can use gunzip, or you can use a command named zcat. They all 3 work alike and produce the same result. You can also use gunzip to restore files that were compressed with the compress command and have an uppercase Z as their extension. Gzip can retrieve a file from a zip archive, but only if there is only one file in that archive. The zip utility can handle several files in the same archive, but gzip can't. Gzip is very much like compress in that it works with one file at a time and uses the limplziv algorithm for compression. Because gzip always performs compression on a file, it's possible for a compressed file to be slightly larger than the original, but this is rare and it's only a few bytes larger when it happens. Gzip and gunzip also have a special relationship with the Linux tar utility, and I'll be showing you that here in a few minutes. These programs were originally written to be an update to compress and uncompress, so they're much newer. You can get the version information with the V option like this. You can also get a list of the command line options, but to do so, you must use the H option this way. And of course, so does gunzip. This lesson is about Uuencode and Uudecode. The 2 U's in front of the name come from the fact that these programs were originally intended to prepare files for transmission from one host to another, that is, a Unix to Unix copy. In fact, there is another utility that's a first cousin to these that's called UUCP, which is sort of an acronym for Unix to Unix copy. The fact is, the Internet can only transmit character data. These routines are not as crucial as they once were because today most programs that send and receive Internet stuff on their own do their own encoding and decoding. So the whole thing has become mostly automatic. But if you want to know what it is they do, you can take a look at Uuencode and Uudecode. Any file can be converted to a set of ASCII characters by assigning ASCII characters to represent numeric values, and that's what Uuencode does. For example, the file in this directory named diff is a binary executable. Running it through Uuencode results in a character form of the file. This example directs the output from Uuencode to standard out and then pipes that into more. There it is, the binary code converted to an ASCII file in this special format. The output from Uuencode can be piped into another application, such as the mail program, for further processing. Or, if you want to create a file containing the encoded form, you can do this. In this example, the cat command lists the file to standard out, and that is piped into Uuencode. The name diffout was included as part of the output and will be the name of the new file when it's extracted from the archive. The encoded data was piped into a file named diffencoded. Now here we have the original file named diff and an encoded version of it named diffencoded. Notice that the encoded version is much larger. That's because each piece of binary data in the original form is now represented by a character. Uuencoded files are always larger. Now, on the Uuencode command line, the name diffout was specified. That will be the name of the new reconstituted file. It could have been the name of the original file, but I used a different name to demonstrate Uudecode. All you have to do is point Uudecode at the encoded file this way. It decoded the information and created the new file with the name that was inside the encoded file. With these two utilities, you can convert any file to ASCII text and back again. There are other ways to use these programs, mainly by piping data in and out of them and through others. If you want to do something like that, check the man page for Uuencode. There are lots of combinations, and you can even specify a different character set for the encoding by changing the numeric system to base 64. This lesson is about a program named SHAR. SHAR, S-H-A-R, is sort of an acronym for Shell Archive, and the SHAR program is used to create what is known as a shell archive. Now this is a shell script that, when run, produces a copy of the original file. Any file, no matter what its original format, can be converted to a shell archive. The process is something like Uuencode in that everything in the original file is converted to ASCII text. In addition, the ASCII text is surrounded by a shell script that will read the text and create a file that is identical to the original. That is, all you have to do is execute the file that comes out of SHAR to get a copy of the original file back again. For example, this is a class file containing the executable code of a Java program. The SHAR command will send a script to standard out, and we can pipe that through more. It even puts some comments at the top, so you'll be able to tell what the script is if you stumble across one somewhere. As you can see, there's quite a bit to the script. And this data format should look familiar to you. It's just like the stuff that comes out of Uuencode. Now, putting a script like this into a file is simple enough. Just pipe the output of SHAR into the file. As you should have suspected, this script is much larger than the original file. Not only has the binary data been converted to character data, but it's also been wrapped in the shell script. Now, I can just delete the original file because I can get it back from the archive. Now this script can be executed just like any other by changing its permissions and running it as a command. Another way to execute the script is to start a shell and use the name of the script on its command line, like this. This same technique can be used to construct scripting for multiple files. As many files as you name on the command line to SHAR will be included as part of the script. If you encapsulate lots of files or large files in a script this way, the script gets very big. But that's okay. If you're going to transmit it over the internet anyway, it would be converted to character data, so the size cost is very small, and you can ignore it. It's a very handy way to send files to someone. You could compress the files before you create the script, or there is an option to have them compressed as you create the script. Depending on the types of files, that could make them a lot smaller. And take a look at the man page. There are many options. There are ways of having char output multiple scripts instead of one large one. There are options for you to do things just about any way you want to. This lesson is about tar. This is probably the most used of all the archiver programs. It's been around for quite a while, and if you know something about where it came from, you'll be able to understand a little more about why it works the way it does. TAR is sort of an acronym for Tape Archive, and it was originally written to copy collections of files and directories to a tape drive. Now, a tape drive is a serial device. While it is possible to randomly access data on a tape drive, it should be obvious that it would be best to write it serially from front to back and to read it from front to wherever you find what you're looking for. And this is the basic philosophy of TAR. When you give TAR a bunch of files to write to an archive, it creates a header block, then it starts writing the files one after the other. Each file has its own header block that specifies the name of the file, how big it is, and some other data about it. That way, when the tape is read serially, the name and size of each file is known at its beginning, and the program can decide whether or not it's the one that it's looking for to be restored. TAR has been around for a long time, and every now and then a new feature is added to it. The result is that there are more options than a normal program should be required to bear. Look at this. So let me give you the quickie tour. There are three basic functions. You can use TAR to create an archive, view the contents of an archive, or extract files from an archive. And although TAR was originally designed to work with a tape drive, it works just as well with a file. As a matter of fact, it's probably where it's most useful. Especially with disk space being as cheap as it is now. I use TAR myself for my daily backups by creating TAR files of directories and storing them on disk drives on other computers on my local network. Let me show you how TAR creates an archive. Here are a couple of directories that contain a bunch of files. I'm going to create a TAR file from these directories. Now, these directories only contain files. There are no subdirectories. But if they did contain subdirectories, all of them would be included in the TAR file. TAR always descends down the directory tree to include every subdirectory and file that it finds. This command will create a TAR file from these two directories. The first letter following the command is taken as the fundamental command. In this example, the letter C is used to create a TAR file. The second option letter is V for verbose. I always use the verbose option with TAR because I like to see what's going on. The third letter is F, which indicates that the next argument on the command line is going to be the name of the TAR file. Without this option and the name of a file, the output from TAR will just come to standard out. That makes it easy to pipe the output of TAR over a communications link or directly to a device, such as a tape drive. Since this command is to create an archive, the rest of the names on the command line are the names of the files and directories to be included. The TAR file is complete. It's quite simple to gzip the TAR file. You just add a Z option to the command line and it's done. When you do this, it's customary to add the gz suffix to the file name. As you can see, this runs a little bit slower, but it makes sense because of the extra job of gzipping as it goes. But you can see the difference. Now the T option is used to list the contents of a tar file. This option is actually easy to remember. Like I said earlier, I always use the verbose option, so the command for viewing is TV. But you also need the F option to name the file. And that's a complete list of the contents. You can do the same thing with the gzipped version by including the Z option. The other fundamental operation is the extraction of the files from a tar file. I'll create an empty directory and put them there. The command line option to extract files is X. The tar files are in the parent directory of this one, and the name of that directory from here is .. so the files can be extracted this way. And here we have the two directories. I'll remove these directories and restore them from the gzipped file. One very important thing about tar: the files you store in the archive will be either relative or absolute path names. The examples I showed you were inserted into the tar file based on relative path names, so the files were restored relative to the current directory. That is, the files and directories in the archive could be restored to any place you want to put them. You can also store things in a tar file based on the absolute path names of the files. An absolute path name always begins with a /, the root directory. Let me clean out this directory and I'll show you what I mean. Now, the archive of these two directories can be created this way. Now this will archive the same two directories, but it will use their complete path names. Notice the full path names are listed as the files go into the tar file. Those path names are also stored in the tar file. These files cannot be restored to another location. No matter where the tar file is located and no matter what the current directory, these files will always come back into a directory named home/arthur/ac/miss and /restore. Okay, that's a quick look at tar and its three fundamental operations. By finagling with the options, you can extract one or two files or one or two directories instead of the whole thing. You should find tar very flexible and very useful.